in this problem, we look at a circle that's inscribed in right triangle ABC, and then we look at a circle that is inscribed in the space left after the inscribed circle. And so the second circle we're going to look at is something like this. Inscribed circles are always difficult to freehand draw. So there's a couple pieces we need to do. First off, we need to find the radius of the first inscribed circle. And there is a nice formula for this, but we'll take you through the process just because we're going to use this theorem. And that is, you can use equal tangents. If you draw in your radius r, then because of the right angle, we get a square in that corner that has side length r. And then we know they're both r because a point A that is tangent to the circle at D and E, those two segments are both r. Now, using equal tangents, we can say that if this length right here is 8 minus r, then this length right here is also 8 minus r, because B is a point outside the circle, and G and E are on the circle. So the equal tangents theorem says that those two lengths are the same. Similarly, we can come up here and call this 6 minus r and this 6 minus r. And so now what we've done is we've created an equation using the hypotenuse of 10, described as 10, and then also as 6 minus r plus 8 minus r. If you solve this equation, I won't take the time to do it, you get r equals 2. So we start by knowing that the radius of this inscribed circle is 2. Then we need to take a look at this circle, and that's what we're going to try to find something out about. And we're going to try to find the radius of it. Right? It says find the radius of that circle. So we do know that this length right here is the radius, and we'll just go ahead and call that radius x for now. And taking a look at this, it would be very convenient if we were able to connect F with the center of that circle, and then with B. And so the first thing we need to do is find out, is that actually possible? Are those 3 points, the center of the circle we just drew, F, the center of the inscribed circle, and B, are they collinear to each other? And it turns out the answer is yes, because F, being an inscribed circle in center of the triangle, must be on the angle bisector, so BF must be an angle bisector. But if we were to draw in any tangent line to our second smaller circle, we'd have a triangle that this circle is an inscribed circle of as well. So B, and let's just call this point P, BP would also have to be the angle bisector of B, because the angle bisectors meet at the center of the inscribed circle. So that means F, P, and B are all collinear. And that is very useful because we can find things out about FB. First off, we know because of the radius of being 2 that EB is going to be 6. So using the Pythagorean theorem, 2 squared plus 6 squared is going to give us FB squared. 2 squared plus 6 squared is 40. Square root of 40 is 2 root 10. And so we know that FB is equal to 2 root 10. So that's really good. Then we also know that FB is going to be this length, 2, plus R plus PB. Well, PB is a value we can find because it's going to be the hypotenuse of a triangle similar to our triangle, that is the 2, 6, 2 square root of 10 triangle. So we can actually find PB, and we can find it in terms of x, because the radius, because the relationship between the FE and the hypotenuse is 2 over 2 root 10. So the relationship between this radius x and PB is going to be the same. And so PB is going to equal 2 root 10x over 2, which turns out to just be root 10x. Because of that, we know that FB is equal to 2 plus x root 10, right? Because PB is x root 10. But we also know that FB equals 2 root 10. Now we can solve. We subtract 2 from both sides and then factor out an x. So x times 1 plus root 10 equals 2 root 10 minus 2. divide through by, and I'm going to make it root 10 plus 1 just because I'm going to use that over here when I simplify my radical. To simplify the radical, you're going to multiply the top and the bottom by root 10 minus 1 because of conjugates. And root 10 plus 1 times root 10 minus 1 equals root 10 squared minus 1, which is 9. Root 10 squared is 10. And then multiplying this out, you're going to get 2 times 10, which is 20. And then 2 root 10 minus 1 is negative 2 root 10. And then you're going to get negative 2 times root 10, which is another negative 2 root 10. And then plus 2. And so it turns out that the radius of this inscribed circle is 22 minus 4 root 10 over 9. And that's the radius of that smaller inscribed circle. Not very pretty or nice, but very calculable.